Well, good morning, everybody, or everybody that's in the room so far. We're going to try and fill the room up a little more than we have at the moment, but I'd like to get us started with our program. So, welcome to the Cleanroom Technology Conference event for 2024. We were reminiscing this morning. This is the 8th event of its kind here in Birmingham in the UK. We started this back in 2017 and has continued every year, even through the COVID years where we were doing it virtually. So we hope this year again builds on the great prestige that we've had through the last few years, and we have 18 fantastic presentations over the course of today and tomorrow. 10 presentations today, 8 tomorrow. So please indulge the presenters as much as you can through the course of the day. My name's Tim Triggs. I have the pleasure today of being the chairman, trying to keep us to time, introducing the presenters, and trying to encourage those from the exhibition hall to come in and listen to the great presentations. I was also reminiscing, it was 35 years ago when I first went into a clean room. So I'm feeling quite old these days. And I started my career building and testing clean rooms with a company called Laminar Flow Systems. I moved into the pharmaceutical industry inside GSK, and then latterly worked in the instrumentation side of the industry, testing and monitoring instrumentation for clean rooms. That was my paid jobs. Really now I'm on the right-hand side of here trying to retire, which is going to be a slow process, probably over the next 35 years. And so I consult for ATI, but part of my role today is working with our Contamination Control Network, the UK Society for Contamination Control, with the Cleanroom Testing and Certification Board International for testing, training and certification of cleanroom testers, and also as a subject matter expert for organisations like the Pharmaceutical, Healthcare and Sciences Society. So still passionate about this industry that we're all a part of, and I want to try and generate that energy and passion within the room today. So here we are again at the National Conference Centre. There is nothing that I am told that is planned to evacuate us during this next day or two. So there are no planned fire events. We are on the ground level here, so exits are out of all of the doors that you see here and straight out onto the car parks for safety. The toilets, if you've not found those, are down one floor. So find some staircases downwards. That's where the gents and ladies' toilets are. One of the important things, I think you've possibly found them already, is the refreshments. So in the middle of the exhibition area is where all the tea, coffee, food and drink will appear at various times through the day. So importantly, we have conference in here, exhibition in the hall next door. So we're just in 2 rooms this year, which should be logistically easier. And of the 18 presentations, many of them will be available to you. So not all. Some prefer to keep their presentations within their corporate entity, but most will be available. So there will be a communication after the event, provided you are registered. You will get a connection from the HPCI team with all the presentations. As they will do, as many of you also do, please share this on social media as you wish. Take photographs, share information, and let's make sure that this event gets some recognition within the industry we're a part of. HPCI team, Brian and the team at the entrance, they put this together, so a big recognition has to go to them to get us all here and registered, and they put cleanroom technology together. The regular communication, the digital media you get, the print journal that you see on a monthly basis. If you're not a subscriber, please subscribe to Cleanroom Technology. That's a continuing media for all of us. This is a 2-day event in the course of our year, but try to be connected on a more continuous basis. The facility, the hosts, always do well here at the conference centre. That's why they've come back here year after year. And Kevin and the team at Hawk always keep us wired up and give us the audio-visual support, so thank you to them as well. OPEC and ANSOR have been the two main sponsors this year, and then the ICCCS, the CCN, the Irish Cleanroom Society, and the Cleanroom Technology Society of Turkey are the four partner organisations for this year, so thank you to all of them as well. And then importantly to you, to delegates and exhibitors. If there are no exhibitors and no delegates, there's nobody to listen to and nobody to communicate and network with. So it's a very important event in the calendar year for Cleanroom technology. I won't go through this in detail. You have the programs, 18 great presenters. We're going to start off here in the morning with Alex Nila very shortly. And we'll go through, it's quite a long day today, so pace yourselves. Take on the refreshments, the drink and the food and the water. We're going through to about 7 p.m. this evening, so please stay with us. There is a quiz. We've never done a quiz here in the UK before. We did it last year in Asia for the first time and it worked really well. Some of you are thinking, yeah, I remember those questions from last year. Some of them were a little dodgy. It was quite competitive, but there is a network event from around 5:40 this evening. HPCI is sponsoring that, so there is a bar, there will be some drinks, some networking, and 3 sessions of a quiz. So think about who you want to team up with and what you all know between you. It's our version of pub quizzing. So we'll do that this evening. So without further ado, I'm going to introduce the first presenter, Alex. So Alex Nila from LaVision. LaVision. Yep. So Alex will come speak to us about cleanroom airflow visualization, but something that's quite new and different, I think, to our cleanrooms. So Alex, please, you're very welcome. Will you take this? Okay, and you're straight up.
Yeah, okay, perfect.
All right.
Cheers. All right. Okay, thanks, Tim, for the introduction. Good morning, everyone. My name is Alex Nila. I'm an application consultant with LaVision UK. And I'd like to start by saying thank you to the organizers for having me on the program today. Today I want to speak a little bit about a novel technique entitled background-oriented Schlieren, a little bit of a tongue twister, so we'll talk about BOSS. Yeah, it makes it for an easier title. And this is a contamination-free approach for cleanroom testing. So you'll see me referring to this flow BOSS technique, and this is something that we developed hopefully as a new technique that might come in handy for airflow tests in cleanroom environments. A little bit about myself. I'm a PhD. I'm based in Brussels. I did my PhD in Belgium, and I was studying fluid structure interaction. I was specializing in a technique called particle image velocimetry, looking at quantifiable fluid flow for ocean engineering applications. And I work for the LaVision UK office. This is a subsidiary of LaVision, a wider group. Our headquarters is in Germany. You can see here our headquarters in Göttingen. And this is a company that's celebrating this year's 35th anniversary. This was a spin-off from the Max Planck Institute in Göttingen. And since its foundation, our company has been dealing with developing state-of-the-art measurement systems. And these are imaging-based measurement systems that we've developed along the years with leading scientists and research groups. We have a lot of collaborations. And we're looking to introduce the latest in image processing algorithms and obviously integrate the latest hardware solutions into these turnkey systems. So we're still dedicated to advancing these state-of-the-art image processing algorithms and developing the next best thing. But at the same time, we're committed to introducing these technologies in an industrial environment and seeing how these technologies can come from academics, where you have these labs where everybody's having a lot of time to play around with optics, with lasers, etc., and coming into an environment where we need something that's easy to use and fast to apply. So we have a lot of different techniques, and we're stretching from the R&D labs all the way to QC and inline testing and production testing. So a little bit of some of the techniques that we deal with. Obviously, a big chunk of it is in fluid mechanics. That's why I'm also working for LaVision, including quantifiable techniques such as PIV, but also qualitative airflow visualization. We also have a big range of activity in combustion research, so looking at everything from combustion species that have to do with engines and general combustion. We're looking at material testing, so material deformation, and this is another quite important part of our product portfolio. And also spray characterization and particle sizing, so for a wide range of sprays that might go from home care and beauty products to industrial and agricultural sprays, including to pharma sprays. So we do have quite a lot of application areas that we're active in, but the main thread is that we're looking at these imaging-based techniques. And how does this relate to kind of clean room environments, and how come we're actually here today? Well, we wanted to develop a technique that alleviates some of the drawbacks of smoke testing, right? We wanted to have, obviously, a technique that addresses the requirement for reducing the cleaning time and effort required after conducting smoke tests. We also wanted to have something that might be useful in a more inline production kind of setting that doesn't affect adjacent areas and rooms that might not be a part of the flow monitoring process. So what we want to aim for is an alternative method, an alternative technique that produces this greater manufacturing agility, that reduces this downtime that is caused by the cleaning time with traditional smoke testing. We also wanted to have a technique where we can use our existing expertise. And as you've seen already, our existing expertise pertains to these quantifying flows. So we wanted to see if we can get anything out of the flow visualization. On the one hand, it's obviously nice to have something that's contamination-free. On the other hand, it would be even nicer if we can also have something where we can put some numbers, for instance, on flow velocity. And we're going to talk about this later on in this presentation. So we came with a technique, so we all obviously needed also to have a sort of name for it, and we kind of went for this smokeless smoke testing. You can see here how this would look like in an actual environment, and you can see a side-by-side comparison of smoke testing and this so-called background-oriented Schlieren or BOS airflow tests. Obviously, there's a need to look at certain different test procedures, test protocols, and also environments where these techniques would be applicable. So we wanted to see if we can have something that is as intuitive to use as classical smoke testing, as easy to use in typical environments, but that can produce something which is contamination-free. And you can see here on this movie some nice examples of identifying recirculation eddies, looking at turbulence, and this is done on the fly. This is done with this so-called flow BOS camera. So we're talking about BOS, we're talking about flow BOS. How does this actually work? What does this entail, and what is the technique based on? Well, this is actually quite an intuitive technique that we're all quite familiar with. We've all experienced this. If we look on a hot summer's day, we look across a highway, for instance, we will see the heat rising from the asphalt, right, which is heated by the sun. This is obviously the so-called mirage effect, and this is a Schlieren approach that is something that we observe, these streaks of warm air rising from a heated surface. Now, in order to quantify this, a technique called Schlieren was developed, but this was actually developed not for fluid flow characterization, but more than 100 years ago, it was developed for inspecting the optical quality of glass. obviously, as you might have guessed it from the name, this was developed in Germany. But then this technique was later adapted and applied for airflow investigations. Particularly NASA, for instance, was looking at pressure gradients. They were looking at using this technique to enhance and visualize pressure gradients, for instance, at the presence of shock waves in supersonic flows. This technique involved a very cumbersome setup. We were talking about high-grade optical mirrors, very expensive mirrors, looking at very small fields of view. So this wasn't scalable at all, and it required very skilled scientists to be able to apply it. However, this was later adapted, and a new technique was introduced. That was originally called synthetic Schlieren, later to be called background-oriented Schlieren by the German aerospace in the so-called DLR in Göttingen, where initial tests were conducted with this technique. Now, how does this work? Well, we're replacing this need for complex mirrors and light sources and knife edge with a static background pattern. And this background pattern can be a multitude of approaches. We can have printed patterns, we can have displayed patterns, we can have projected patterns, or even the natural pattern. And actually, this background-oriented Schlieren approach was first deployed using natural patterns. NASA flew a camera 30,000 feet and took images of a natural background from the desert and flew these fighter jets to visualize the shock waves emanating from these fighter jets. So this is how it was obviously used for these large-scale outdoor measurements. But we are typically interested in also applying this indoors, etc. So we would have these sort of patterns. And the main feature of these patterns is that we want to have a randomness to them and have a good contrast of the features. We're imaging these patterns with the camera. And as soon as we introduce a refractive index change along the line of sight, this will deflect the light ray between the camera and the background pattern, introducing this apparent displacement, right? This is something that we can also see by naked eye when we're looking at these heat waves generated from a hot surface. Now, what we're doing is we're using then a smart algorithm to transform these displacements and enhance these displacements into something that we can easily use as an intuitive flow visualization technique. Now, one thing to note is that also this refractive index change can be introduced by several factors. We're not talking here only about heat changes, so temperature gradients, but we can also be looking at density gradients as well as pressure gradients. So we have quite a few different sources of this BOS signal that can occur. Okay? So based on this, of course, we saw that we can apply it on a number of different applications, but more importantly, on a number of different scales. So we can really scale this technique up very easily. We wanted to aim for having a quick setup, and obviously this provides us with a quick setup as we only need this background pattern and the camera. And we didn't want to bother with a lot of alignment processes like with classical Schlieren, right? Now, of course, this technique can be used for a lot of different processes, from mixing monitoring to obviously airflow visualization and even leakage detection. But we also wanted to go a step beyond and look at some quantitative output from the technique. And this is where we'll talk later on in this presentation. We can actually apply some other smart algorithms to use the signal to get some quantifiable flow velocity measurements from the data. Now, how would this look like in practice? Well, we have here just a simple lab setup, just showing the principle. We have the pattern in this case is displayed. So we have a screen that's displaying the background pattern, and then we have this air gun that is just used, and then we have the flow BOS camera showing us this live BOS movie. Now, one critical part is that we have the means of not only recording a live movie that you can use to monitor the process as you're in the test setup, but actually save this and also do further high-quality rendering after the fact that might be able to get you even higher sensitivity of the data from the same raw movie. Now, as you've seen there, we have an introduction of a seeding gas. This is introducing the density change, the density gradients that we're looking to visualize with the BOS signal. And obviously, we wanted to have a look at a few different gases. There's a multitude of choices that we can consider. And obviously, what we wanted to go for is to have a gas that is non-toxic and non-reactive. This is the key point to have it useful in a clean room environment. But at the same time, we wanted to develop this so-called BOS air that has the same weight as air. Obviously, when we're talking about density changes, we could easily see how different gases would either flow down or flow up because they have a different density. But if we have a mixture of noble gases with some oxygen, we can reach the same weight as air. So we don't have any inertia of the gas as we're introducing it into the flow, right? So it really becomes a tracer gas. Now, when we talk about the flow BOS camera, this would be looking something like that, where a clean room version is illustrated here so that you can see kind of IP64 ingress protection, housing, easy to clean camera. But inside, and this is a key factor, we have a high dynamic range camera. That allows us to have a very sensitive system, right? This high dynamic range of the camera allows us to be quite sensitive and have a high dynamic range of the signal later on. Autofocus lens making it easy to adjust for different working distances and different fields of view, of course. And then this built-in display to have this live monitoring of the application. So this is the basics of how this technique works and how we thought about the layout. But obviously, what is important, especially for you, is to see how this works in the field and how this would look like in actual clean room environments. So I'm going to talk a little bit about some application. I'm going to start off with this room return airflow test. This is obviously a very, very simple test where we first looked at just smoke testing to begin with. We wanted to compare with this smoke test and see how the flow BOS approach would be able to produce similar sort of results. So we saw, okay, everything is pretty much where it needs to be, and we went ahead and did some flow BOS visualization on the same room return. What you see here is a seeding rake. So we're introducing this BOS air through the seeding rake in a very similar fashion that you already know from smoke visualization. So we have different a multitude of nozzles, and we're introducing the BOS air, and here you see the live processed image or live movie with the BOS signal. One thing to note here is that we're actually projecting a pattern. So we didn't print out the pattern, but we're actually projecting the pattern on the floor, and this is what we're using as a background pattern in this case. Another example, here we're looking at RABs, and we're looking at the gate between the sections. So we're introducing, again, the BOS air. You can see here the camera looking onto a displayed pattern in the background. So again, even though we have a lot of things going on here, we have a lot of structures in between the camera and the background pattern, we do manage to have a clear line of sight. So we do manage to see the BOS signal quite nicely. Now, one important factor is that, again, because we're not only looking at density changes to produce a BOS signal, we're also looking at temperature changes. We also had, in the same environment, we had a case where we were using the heat signature from the device to actually visualize that. And here you see a nice switch over to a different color scheme where we're actually seeing Schlieren produced by the heat generated from this enclosure. All right, another application example is this clean room in clean room concept. And this is something where the main focus was to test out different optimization of the clean room environment, including the workstation and also in the presence of an operator. And in this case, we had these measurements conducted in Switzerland where we had different positioning of the cameras and background patterns in order to achieve flow visualization at these different locations, which are illustrated with a red dashed line, right? So we had a few different scenes that we wanted to accomplish, and you can see them here for 3 different examples. right, in the presence of objects, and obviously the main point was to see how to optimize the positioning of these objects. But here you see also a movie in the presence of an operator. And what is interesting here is that we can actually visualize the two signatures. We can see the density effects from the boss here, which is being introduced, but we can actually also see the heat signature from the operator itself. So we can see the heat emanated from their body. And you can easily get a sense of how sensitive and powerful this technique can be, and how it can help us see more than just one simple effect, such as density changes. Another thing I would point out is that we can easily switch between what our eye would observe, so what you can see with the naked eye, and the pure boss signal. So we can have a closer look at what Schlieren is caused by which effect, and get a better sense and amplify the signal in post-processing. All right, so in terms of thermal flows, obviously for clean rooms, the density gradients are quite important, and that's where we use this boss here. But for thermal flows, we also have a very wide range of application areas. This was actually a movie put together by our managing director about 2 days into the COVID pandemic, when all the offices had to be shut down, nobody was there. He went into the lab and put together this quick boss visualization to show the effect of using a face covering. Of course, from this, there were a lot of investigations, and a lot of our customers used this technique to really dig deep into face covering investigations, looking at the effects of different face masks and visualizing these airflows. So obviously here we're looking at just the plumes generated when breathing, exhaling, coughing, sneezing, and then how this is mitigated by the use of a face mask. So this was picked up on quite quickly, but there were a lot of other application areas that we're able to look at with the flow boss approach, and this is one of them, just heat generated from a projector. Obviously, as I mentioned, the sensitivity of the technique is quite high, so you can see here just the heat generated from a human hand, how it can be visualized with flow boss, obviously on the fly. Yeah, another example here, just a simple candle flame ignition extension using CO2, and obviously this meant that there was a lot of interest in kind of HVAC industries, where they looked even at the AC effects in an automobile. Another example here, thermal flow of a compounder. This was a very interesting application. They were looking at optimizing the positioning of this extractor. And this obviously can be done on the fly, because you can have this live boss signal, and you can change the position to see where you get the highest efficiency of the extraction. Now, as I mentioned at the beginning of this talk, we wanted to also see the potential for getting quantifiable results. And again, coming back to these COVID times, we had a lot of our customers look to use BOSS for qualitative investigations. One such group was that of Dr. Ignacio Viola in Edinburgh, who really did a very systematic test looking at the effect of face coverings. They also developed a mannequin to have a very reproducible test. And they were looking to quantify or to qualify the airflow using BOSS, but also extract a little bit more information. And for this, we're using a technique called particle image velocimetry, or in short, PIV, which typically works by seeding the airflow or liquid flow with tracer particles that follow that flow. We illuminate these particles, and we record images of these particles at different moments in time, and then we track these particles to get velocity information. So we're looking at 2D or 3D vector fields that would look something like the arrows that you see overlaid onto this BOSS image. So we decided, okay, why not actually use the BOSS images instead of these contamination-introduced tracer particles, and use the BOSS images to look to quantify the fluid flow. And this is what we did in this particular case. To look a little bit more in detail, this was an example where we used CO2 to see this air flow produced by a fan. And we had the BOS signal, and obviously by applying our PIV algorithms, we end up with something that we named Schlieren image velocimetry. And this is basically showing us this vector field associated with velocity, magnitude, and direction that is given by the actual Schlieren in the images. Now, why is this important? Is because we can visualize, we can imagine how we can use this for having a sort of virtual anemometer, right? We're all familiar with these point-wise devices that we can introduce in the flow to quantify our flow, but this can be done after the fact on full field images in the flow, or even live on the BOS images as we're processing them. So we would have something like this where we see the flow BOS signal, and then we can choose a region of interest where we can get velocity, magnitude, and direction. Obviously, this would make it quite an interesting proposition to get in terms of not only velocity, magnitude, but also some information about the flow structure once we couple it with this flow BOS approach. That means that we can have this reproducible and traceable, right, measurement technique that is a little bit more easy to understand rather than a point-wise measurement that is given by a device, a handheld device. All right, moving on to some conclusions. So obviously, we saw that there's some benefits to this kind of smokeless flow BOS testing. We set out to aim to not have these smoke residues and therefore to shorten downtime of production areas and obviously ultimately lead to cost savings. There are, of course, limitations of the technique. We don't foresee that this will completely replace smoke testing, particularly because there is this requirement of having a line of sight approach. So we need to see the background pattern as we're applying it in, for instance, a cleanroom environment. So not all of the scenes that we might be testing can be supplemented with flow BOS. However, we see this as a complementary technique, and we're certainly going to be looking forward to also get your feedback into how you could potentially see this technique being applied in your specific test cases, and how this could actually help slow down the downtime associated with typical airflow tests as it is right now. Obviously, we're also seeing some potential, right? Some potential in inline testing, because since this is not introducing any contamination, we could also see perhaps this as being something that can be a round-the-clock flow monitoring process that can pinpoint to some issues in production. Now, I know that this forum is probably more focused on the part of the presentation so far, but I wanted to also introduce a couple of slides to show some potential, something to look forward to and see if this is something that might be of interest to. We've applied this flow BOS measurement also in conjunction with our tomographic reconstruction capabilities. So obviously, in flow measurements, we have the means of looking at fluid velocity in a two-dimensional slice, but we also have algorithms that allow us to do a 3D reconstruction of the flow field. As long as we have a 3D illumination, we're taking images from different perspectives, and we can recombine this into a volumetric reconstruction. So what we decided was to apply the same principle to the BOS approach. And here we have different cameras. These are scientific imaging cameras, 6 cameras, and background patterns corresponding to each of the cameras. And then we're having some airflow introduced, a burner of some sort. And then we're taking these independent 6 views that you can see right here, and we're running this through a tomographic reconstruction algorithm. Now, the key benefit of this is that on the one hand, we can get this 3D shape of the plume generated, and it could be a thermal plume, it can be just a density change plume. But at the same time, we can get physical quantities such as temperature, right? So in this case, obviously, we have a temperature difference, and we can visualize this temperature difference on the reconstructed results. So obviously, you can see that this is a little bit more involved. This is a little bit more in the scientific realm, but this can have potential to actually give us even more quantifiable results after the fact. And here are just some slides where we have just a couple of examples, yeah, just with a coffee cup and a Bunsen burner. And this is just showing how we can get absolute temperature and look at things like concentration or mixing. Okay, so maybe that was the sign that I need to wrap up. And yes, you can visit us on stand G8 for looking at also this camera in action. And the floor is open for questions. Thank you.
Oh, don't look at me, it's not me either. Alex, thank you very much. Well, that was a warming up presentation, right? Straight in with something that's a very novel technology that's perhaps never been seen in a clean room before, but airflow visualization is certainly something that's a hot topic for us to talk about in clean room for airflow visualization. So would anybody like to put a question or questions to Alex? I'm just going to grab a microphone if we have any at the back. Thanks, Kevin. Here's a very left field question. Was there?
Yeah, apologies, but this technology seems quite interesting. So have you heard from maybe the automotive industry, particularly with EVs, with their drag coefficients, or even motorsport and Formula One, with their limits on wind tunnel and things like that? This would be an alternative technique that's just, for me, seems pretty interesting.
Indeed, I mean, that's a very good point. We actually are already having quite a few systems in the automotive industry and even more so in F1 industry. Obviously, they're very keen to quantify their to validate their CFD simulations, the numerical simulations on fluid flow. There they actually have more quantifiable measurement systems like this PIV systems that I mentioned. And they use this in an automated way, so we kind of introduce this in their wind tunnel testing environments, and it's pretty much automated to run along with their other load sensor measurements, et cetera, et cetera. But certainly, I think there's a scope, and we have seen this being done as well, at least for these AC measurements, so looking at the airflows inside the cabin in a car. And for that, obviously having this technique makes it a much easier to use approach. It doesn't require the setup time that we have with PIV. So yes, there's a lot of potential, and there's also potential to look at different stages, whether we're just looking at the simple to use technique that gives us an idea of what's going on, all the way to the more advanced kind of in detail 3D reconstruction with very accurate numbers associated to them.
You were first up, Tony. You're going to have to be fast.
Just a practical question, really. Are you thinking that you would sell this as a service, or would people buy the cameras and do it themselves as a...
A little bit of both. I mean, the company's business model has been providing systems, right, turnkey systems, and historically it's been around providing systems to academics. But we're now, as I mentioned, going more and more into industrial settings where we see that providing a service where we have the ability to go in, do measurements, obviously having the expertise to do this in a fast and efficient way is something that we're equipped to do. So I think it's a little bit of both. I can certainly see that providing it as a service might be a little bit more interesting to begin with, but we do have partners that already have the system and apply it in their labs and looking to work with us to kind of get the most out of their system. And I think ultimately, if this is fulfilling as much as they would like to from their test scenarios, and they have the confidence that this is something that they can easily apply technician can do in the lab without the need for a LaVision person to be there, I'm sure that this can also have potential further down the line.
Just in the spirit as well of networking, introducing yourself, and that was Tony Horsfield from ISO Cleanroom, but whenever you take the microphone, please introduce yourself, at least so Alex can track you down later if he needs to.
So Alex, thank you. Gordon Farquharson, speaking later today. I was a little bit confused about boss gas. So, because you showed some seeding with CO2 and so on, and then you talked to, can you just clarify whether you are always using something to assist the imaging?
Right, that's a very good question. We're for cleanroom tests where we would go in, for instance, to provide a service or to sell a system, we would always recommend the boss gas. But sometimes people are interested in looking at the density gradient introduced by a specific gas, for instance, helium or hydrogen or even methane or something else. This becomes quite attractive, whether that's for leakage detection or for leakage detection or micro leakage detection. So whether we're looking at small scale or really outdoors, huge installations, and looking at, for instance, hydrogen escape valves and equipment. We're working together with a customer who's looking to use their methane distribution network to distribute hydrogen, and we recently performed outdoor tests with a long distance version of this FlowBoss camera. So using as background pattern just actually a rock quarry and just the vegetation there. There you do have a dynamic system, right? So as I mentioned, you want to aim for having a static background pattern. Obviously, measuring outdoors, things happen, wind blows, and so on. So we developed this long-distance camera, which is actually using a stereo vision approach to actually compensate for this moving natural background there. So yeah, in that case, it's actually hydrogen, so it's even. But for clean room, coming back to clean rooms, we would always look at this dedicated boss gas.
So Alex, just as I pass the microphone to the next question, the boss gas, therefore, is a reagent that you're introducing into the clean room.
Yes.
But it is gaseous, it's molecular, not particulate.
Exactly.
You spoke about smokeless smoke testing.
Yes.
Is the boss gas proven and does not have any contamination?
Exactly. So it's a mixture of noble gases, so it's non-toxic, non-reactive, and yeah, wouldn't introduce any particulates.
There was a...
Thank you, that was excellent. I have loads of questions, but I won't ask them now. But I just have one really, about have you been talking to the isolator vendors and the filling line vendors? Because this is really revolutionary if you look at how archaic what people do at the moment is. Right.
I mean, this is one of the reasons why I'm here. We're hoping to get more and more in touch, because obviously for us it's a new market, a new industry, and we're trying to get, we are a little bit more advanced, I would say, in our offices in Germany and in the German market, because that's where we're also a little bit involved in the regulatory process. But certainly, especially here in the UK, we want to get more feedback to see how this can be applied and really get the sense of how people can actually make use of this.
That was Kevin Smith from IPS as well. So I'm going to keep trying to get that. We'll all know everybody by the end of the 2 days. There was one more question we're going to take from over here.
Thank you. I'm Chris Morgan from ATMP Solutions. You were saying that you're able to project the background image. Are there any limitations onto the surface you can? So does it have to be a flat surface? Can it be clear, or would it need to be opaque?
That's a very good question. So there's different ways of projecting the pattern, and we have, well, the most common ways, let's say, are with an LED projector, in which case we are a little bit limited as to what we can do, because we would ideally want to have indeed a flat, non-reflective surface to have a nice signal. There's also, actually in that example that I showed you, That was a laser projected speckle pattern. That has some other advantages and can work well also with more complex shapes, more different textures, and etc. So there are a few different approaches that we can go with that. Yeah.
Thank you.
Thank you. Okay, an interesting topic. I think there are probably many more questions. LaVision have an exhibition stand here.
G8.
So G8, if you have any more questions for Alex across the course of today or tomorrow, then please follow that up. But Alex, thank you again. Really interesting presentation.
Thank you.
Thank you.